Welcome to lecture 26. In this lecture, we will be discussing on synchronous DRAM. So, as the name suggests, synchronous, so it is synchronized with clock. So, SDRAM, so synchronous DRAM, we will be commonly saying SDRAM, is commonly used name for various kinds of dynamic RAM that are synchronized with clock. So, all such kind of DRAM that are synchronized with clock. In the previous lecture, we have seen asynchronous DRAM where there is no concept of clock. The module which is connected to the memory has to take care of that. But in this case, here it is synchronized with clock. The structure of this memory is same as asynchronous DRAM, and the concepts were also known from this 70s, but it was developed in the year 1993. And by the year 2000, almost all kinds of dynamic RAM were replaced by SDRAM. So, there was no asynchronous DRAM anymore. Now, let us see this, the internal organization of SDRAM chip. As I said, the internal organization of SDRAM is very similar to asynchronous DRAM, but it is having some more features. So, you can see that the row and column address can be provided. So, once we apply a row address, it is that particular address go to row decoder and a particular cell get selected. But here you see we have column address counter. So, instead of column address latch, there is a counter which will be used to count to the next column for faster access. And the read write circuit and these latches are connected to the data input register and data output register. So, data input register will be required when we have to transfer a data from a data bus to this particular cell. So, that will come through data input register, and if we want to output something from this chip to data output register, then it will be outputted through data output register. Along with this, we have a mode register and timing control, where the clock is provided. Other signals like RAS and CAS, RASH and cache are also provided, and two more signals, that is read write and chip select. These are also provided here. Apart from this, we have a inbuilt refresh counter that refreshes the rows of these cells periodically. So, this overall diagram shows the internal organization of SDRAM, which we can say that it is very much similar to asynchronous DRAM with some more features, like we have a data input register, data output register, we have a column address counter instead of column address latch, we have a clock involved here, and we have a mode register that we will be seeing what is the purpose of that particular register. So, in SDRAM, the address and data connections are buffered by registers. We have seen that. The output of individual sense amplifier is connected to a latch. So, here the output of individual sense amplifier is connected to a latch. Mode register is present, and what it does is it can be set to operate the memory chip in different modes. We will be seeing that this mode register is very much important, and it can be used for speeding up. We are always trying to make memory faster such that the memory and processor speed gap can be minimized. So, these are few things that are added in synchronous DRAM to make this happen. So, mode register is present, which can be set to operate the memory chip in various modes. To select successive columns, it is not required to provide externally pulses generated on cache line. What do you mean by that? You recall our previous discussion, where we said that the various one row can be selected, and for selecting the data from different columns, we give a column address, then we give the next column address, and so on. So, for giving a column address, a signal cache signal line is activated and that column gets selected. But here the successive columns can be is not required to provide externally generated cache. So, we have a column counter inside that will help internally to generate the required signals. So, this column counter will be used internally, which will be helpful in generating the signals to select various columns. Now, let us see what happens for read and write operations. So, for read operation, the row address is applied first, and in response to the column address, the data present in the latches of the selected columns are transferred to the data output registers, and then the data is available in the data bus. So, what happens in the same way for reading a cell value, we apply a column address, we apply a row address first, and then we apply a column address. In response to that particular column address, the column data are selected and it is stored in the data output register. In this data output register, then it is transferred to the data lines finally. Then the data will be available on the data lines, that is the data bus, and then it goes to the processor. Similarly, for write operation, the row address is applied first, and in response to the column address, the data present in the data bus is made available to the latches through the data input register, and then finally the data is written to the particular cell. So, for reading and for writing, the required cell needs to be selected. After the cell gets selected, the particular data will be read through this data output register or will be written through this data input register. Now, let us see what is this burst mode transfer. We already discussed about fast page mode, where we select a particular row and a particular column, and then we need not have to select that particular row again, rather next data can be available just by incrementing the column addresses. So, here also we will see that how this burst mode transfer happens. As in fast page mode, after the column address is applied, the data from successive column addresses are read out or written into. So, for read it is read out and for writing it is written into. In the same way, burst operation of different length can be specified. So, burst operation means burst of data, a set of words are transferred. So, here different length we can specify the how many words we want to transfer. So, for the burst mode transfer, different length can be specified. This uses the same block transfer capability of the fast page mode. So, whatever we discussed in the fast page mode, this block transfer mode also uses the same feature. So, what happens here, the control signals required are provided internally by the column counter and clock signals, as a clock is also associated with it. So, the control signals that are required for this purpose are provided internally by columns, by the column counter and the clock signals. New set of data are available in the data lines after every clock cycle. So, after every clock cycle, so one clock cycle will be required to get the next set of data. All the operations are triggered at the rising edge of the clock. So, when SRAM came, these are the features. All operations are triggered at the rising edge of the clock, but we will see that when the advancement progresses, then this has changed, and we could do data transfer both in the rising edge as well as in the falling edge. It also has a built-in refresh circuitry, and refresh counter is part of it. So, there is a built-in refresh circuitry that refreshes the different rows of the cell of the memory chip. Now, we must know that the standardization of this SDRAM. So, see, when some products are generally built, so there must be some standardization, so that different companies, when they build that particular system, that can be used by others. So, there should be a standardization. So, we standardize. So, this is the standard, you have to make the chips using such standard. So, SDRAM families are standardized by Joint Electron Device Engineering Council, we call it JEDC. So, various DDR-X, DDR stands for double data rate, X stands for it can be 2, it can be 3, it can be 4 and so on. So, various DDR-X standards have been formulated and published by JEDC, and the board, which are board manufacturers who are building these memory chips, must comply to this standard. So, whichever chip is produced must be complied with JEDC standard. Now, let us see various types of SDRAM. When SDRAM came into market, it was single data rate SDRAM. It is called SDR, SDRAM. What it can do? It can accept one command and transfer one word of data per clock cycle. So, in one clock cycle, it can only transfer one data. One data item can be transferred in one clock cycle. That is why it is called single data rate. Data transferred typically on the rising edge of the clock. So, in such kind of thing, in the rising edge of the clock, the data is transferred. Now, you see this diagram where it shows SDR clock. So, clock is coming, and you see this is the SDR data, SDR data. So, here this data is transferred in the rising edge of the clock. Only one data is transferred. So, this is called single data rate. Let us move on with double data rate SDRAM, which is called DDR, and it transferred data on both rising edge and falling edge of the clock. So, data transfer takes place both on the rising edge as well as on the falling edge. So, we see that within a clock, two data are transferred, one on the rising edge, another on the falling edge. Okay. So, these types of SDRAM are called double data rate RAM. DDR RAM was launched in 2000, and then with time various versions of DDR RAM, DDR SDRAM came into market. So, DDR2 came in 2003, DDR3 came in 2007, DDR4 took 7 more years to come, and people are also saying that DDR5 is going to come in near future. Now, let us see what is DDR2. Now, we see that this is our memory, and internally there are 64-bit data bus. So, the internal bus width also grows with the newer generation of DDR RAM. So, with newer generation we see that the internal data bus also grows, and the clock speed is 133 megahertz. This is the internal clock of the memory. It has got a controller, and in double data rate RAM, this bus clock must be twice this. So, if the bus clock has to be twice this, it should be 266. Now, and the data transfer will takes place both twice in the falling edge and in the rising edge as well as in the falling edge. Now, let us see how this calculation is actually happening. So, internal clock is 133 megahertz, the bus clock is double of that, and we have to calculate the transfer rate. Let us see this. Now, in 1 second, it is 266 megahertz, 266 M clocks will be coming. So, if 266 M clocks will be coming, and in each clock there is a rising edge and there is a falling edge. So, 2 into 266 M clock edges will be there total, one rising and one falling. One is the rising edge, another is the falling edge. And in each rising edge and in each falling edge, 64 bits of data will be transferred. So, a total of 2 into 266 into 64 bits will be transferred. If you want to convert this into bytes, it will be 2 into 266 into 64 divided by 8, these many bytes. So, that comes down to, the transfer rate comes down to 4.26 gigabits per second in case of DDR2. So, total clock frequency is 266 and these many transfers are taking place. Now, let us see what happens in DDR3. Now, DDR3, the internal clock is still this, but now this bus clock has become 533. Now, bus clock has become 533 means you have how many clocks in between? You have 4 clocks here. And so, the width is 64, but you need to have more number of this data internal bus between memory and controller should be more. So, we have 8 here, because if there are 4, then 1 in the rising edge, 1 in the falling edge. So, in the same way we can calculate it. So, it will be 2 into 533 megahertz now into, and each time there will be 64 bit of data will be transferred. If you divide it by 8, you will get 8.53 gigabits per second. So, from DDR2 to DDR3, it was 4.26, now it is 8.53. So, it is doubling almost the transfer rate. That is what we require. We need to have faster memories. Similarly, in DDR4, this is 4 times, and then you have 16 such data buses in between, and here you will multiply 2 into this 1067 into 64, because each time 64 bits of data will be transferred, divided by 8, which is roughly coming around to 17.06 gigabits per second. So, as we move on, the transfer rate is increasing, transfer rate is becoming faster. We are getting the transfer rate is actually decreasing. So, we are getting the data much faster. So, across generation, the DDR for the DDR SDRAM, so we can see that the internal clock frequency has increased, and as the internal clock frequency has increased, in the same way bus clock has also increased, and in turn finally this transfer rate has become very fast. So we have very high transfer rate. This is a dual inline memory module. So these are the slots where these memory modules can be fit in. A dual inline memory module consists of number of DRAM ICs. So you can have number of DRAM ICs put in these places, and these modules are mounted on a PCB and designed for use in PCs, workstations or servers. So inside the PC you will be finding that there are some slots which can be put in there. You can put in there the memory chip. So this dual inline memory module have separate electrical contacts on each side of the module and has a 64-bit data path. So on each side of the module, on this side as well as on the other side, it has 64-bit data path. Now this is one thing we must know, that the DDR memory modules across generations may not be compatible. So you see that this and this, so DDR, DDR2 and DDR4 are compatible almost, but DDR3 is not compatible. They may have notches in different position. So the notches may not be in the same position. So if a particular slot where we are using DDR3, we may not be able to use DDR4. Now to summarize what we discussed about various DDR generations, so SDR SDRAM, that is single data rate SDRAM, can transfer 1 word of data per clock cycle. In 1 clock cycle, only 1 word can be transferred. DDR SDRAM can transfer 2 words per clock cycle, that is double data rate. Now double data rate 2, that means 4. Double, it is double data rate and this is 2. So DDR2 SDRAM doubles the minimum read or write unit again to 4 consecutive words per clock cycle. In DDR3 it is 8 consecutive words per clock cycle, and DDR4 extend the trend again to 16 consecutive words per clock cycle. It is expected that, it was expected because now it is further, in March 2007 a DDR5 standard is under development and has been announced, but still it will take a little time to come to the market. So this is the speed of DDR memories across generations. So across years we have data till 2012. This is how the chip size has grown. These are the types of DDR memories that we were using, and this is the slowest DRAM that were available, and this is the fastest DRAM that are available. And you see finally the cache transfer time, because cache is very important, through which will actually determine finally the transfer rate, because we once we select a row, then we just give different columns address to get the data. And finally, the total cycle time comes to this. So, DDR3 with 8 GB chip size has got a cycle time of 31 nanosecond. So, by this we came to end of lecture 26, where we discussed about synchronous DRAM and the various kind of synchronous DRAM that are there in market, that are used today to make the bridge the speed gap between processor and memory. We will see further that how we can now build larger memories from smaller memory chips in the next lecture. Thank you.